Good evening, everyone, and welcome to the Herschel Society. First thing is check everyone online can hear me. So a few thumbs up might help. Okay, this is a lecture for the Herschel Society in the Bath Royal Literary and Scientific Institution. The title is 21 centimetre Radio Cosmology with the Square Kilometre Array, What Happened After the Big Bang? And the lecturer is Dr. Eloy de Lera Acedo of the University of Cambridge. I'm Tony Symes and I organise the lectures for the Herschel Society. There's somebody I think needs to mute because I can hear some background noise. As you've been warned, the lecture is being recorded. For those people that are in the room at the Bath, two people to admit here, let's just let them in. Right. For those people in the room, if the fire alarm sounds, you need to exit the way you came and assemble near the obelisk in Queen's Square. If that way out is all on fire, then you can go to the back and out through the Lonsdale room, down the stairs in number 18, and out through that exit. Please note that the Brilsey is still encouraging COVID precautions, mask wearing and distancing. As always, for the remote audience, please double check that you're on mute and with video off during the lecture. You can turn your microphone and video stream back on again for the Q&A session. We're now starting our summer break from lectures, so the next lecture planned for the Herschel Society and the BRSI will be on Friday the 2nd of September. For this, we're going to have Katrin Rayner Evans, who is a fellow of the Royal Astronomical Society, talking about exploring astronomy and space through philately, a brief introduction. Philately, of course, is stamp collecting. Back to tonight's lecture. The story behind this is it started with an offer from a previous lecturer, Dr. Case Carrells, to give us a lecture on the Square Kilometre Array. He'd previously given us a good lecture on the search for dark matter. However, he later withdrew, saying that he decided to leave astrophysics for a career in music. This prompted me to seek another lecturer on this most interesting subject, so I contacted the SKA outreach team, who I'm delighted to say introduced me to Dr. de Lera Acedo. He's an STFC Ernest Rutherford Fellow at the Cavendish Astrophysics Laboratory of the University of Cambridge, from where he leads the Cavendish Radio Cosmology group and the REACH, the Radio Experiment for the Analysis of Cosmic Hydrogen project. Dr. de Lera Acedo's career started designing radio antennas and modeling and calibration techniques for the Square Kilometre Array telescope, and over the last decade has transitioned to cosmology research of the early epochs of the universe using highly precise calibrated radiometers. Let me hand over to Dr. de Lera Acedo.
Thank you very much. Thank you indeed for the invitation to present today my work to all of you and talk to you about something that is, I think, for me at least, very exciting, which is what the Square Kilometre Array, the largest radio telescope in the making, is going to be able to tell us about the early universe. It's going to be able to tell us many things, but the ones that I am most interested on are the ones the telescope is going to be able to tell us about the very early epochs of the universe. So I hope by the end of this talk, I have convinced you, or I have at least informed you a bit more about why the SKA is worthwhile doing and what is it that is going to tell us about those early days, figuratively, early epochs of the universe, which are one of the missing pieces in the puzzle of the history of the universe. So before that, anyway, let me start by introducing a bit what we do in Cambridge, who is doing astrophysics and astronomy in Cambridge, where my research team fits, and how do we, how are we part of a mega project like the Square Kilometre Array. Since I didn't know the background of everyone attending the talk, I thought that it would be probably good to anyway give a short introduction or a brief introduction to the history of radio astronomy, and then go into the meat of the talk, which is first of all explain what is this missing piece in the puzzle of the history of the universe, which is the first lights. How do we actually detect and study the light from the very first stars to appear in the universe, and why we haven't done it yet? And then the last part is how the SKA, the Square Kilometre Array telescope, is going to be able to do this for us in a few years from now, hopefully. So astronomy and astrophysics in Cambridge is actually done in 4 different places.
Right, now, do I need to go into the Zoom settings?
No, it'll be
The first place is Cavendish Astrophysics, which is where I belong. That's the institute I'm part of. Cavendish Astrophysics is one of the subgroups in the Cavendish Physics Laboratory, and we are very focused on experimental and observational astrophysics. We are in a part of the city west of Cambridge, for those that have been in Cambridge, that has other 2 institutes next to each other, which are the Kavli Institute for Cosmology in Cambridge, which is basically a continuation of the Cavendish, and then finally the Institute of Astronomy, which is a department on its own. And a little bit closer to the center of town, we have the Department of Applied Mathematics and Theoretical Physics. As the name indicates, they are a bit more focused on theoretical matters, but also involved with astrophysics and cosmology. Anyway, Cavendish Astrophysics, where which I'm part of, is a mix of physicists and engineers, and we design, develop, and operate experiments for radio astronomy. As I said, our focus is mostly on the experimentation in the observation. It is the place that is considered to be the birth of most of modern radio astronomy, and especially the Earth rotation aperture synthesis and the discovery of pulsars. So as a lot of you will probably be aware, that actually was worthy of a Nobel Prize for Martin Ryle, the founder of the radio astronomy group, and then another Nobel Prize for Anthony Hughes for the discovery of pulsars in what is known as the first golden ages of radio astronomy. Anyway, and since 2019, we have a 3rd Nobel Prize in the group, which is Didier Queloz for his discovery of the first exoplanet, first planet orbiting a star outside of the solar system that he did when he was a PhD student in Switzerland. We also host the Muller Radio Astronomy Observatory, which is only 5 miles southwest of Cambridge, and there, if you're ever around, please contact me, because we will try to see if we can actually take you around the grounds, where you will see both historical telescopes like the 3C, or even we could still see a bit of the pulsar array that was used to discover the first pulsar, although it wasn't called the pulsar array at the time. 1 mile telescopes, control rooms, and then on to modern telescopes like the Arc-Minute Microkelvin Imager, AMI, which has 2 components, a large array and a smaller array, as well as an antenna, part of the eMerlin network, which is the largest one on the site, 32 meters across. But furthermore, you will be able to see prototypes of the Square Kilometre Array antennas, both for the low frequency and mid frequency aperture arrays, as well as other antennas of other modern radio telescopes. And my research team, as Anthony explained, is the Cavendish Radio Cosmology. We are, as you can see, 12 people plus myself, and of course what we are trying to do is do cosmology using radio telescopes with a special focus on studying and detecting radio waves from the infant universe. Right, so Let's move to the next second point of my presentation, which was about this brief introduction, history of radio astronomy. I think in this audience, everyone will know that the sky can be observed in many different wavelengths. And if we look at the sky in optical wavelengths or in radio wavelengths, like in this case here at 21 centimeter, 1.42 gigahertz, which is natural rest frequency of hydrogen, we can see many different things and learn many different things about the physics that govern the evolution of the universe. So we have to then use different instruments as well, optical telescopes or radio telescopes that can detect long wavelength electromagnetic emission in the radio spectrum. And this is a very popular poster picture where we can actually see how the Milky Way is seen at different wavelengths, at different frequencies, all the way from the radio spectrum up to gamma rays going through optical frequencies, etc. And you can see that it's not only different colors and different structure, but it can actually tell us quite a few different things about what's happening there. Another important picture for the presentation today is a compressed picture of the history of the universe. I'm going to show several plots today that resemble a little bit this picture, even though they are not identical, but I want everyone to be familiar with it, in which we have, I guess, cartoonish picture of the history of the universe with the Big Bang on the very left, going through inflation, eventually the emission of the cosmic microwave background that started propagating through the universe, birth of first stars, and then galaxies, and then planets, and then up to the present day in the very right. Okay, so how did radio astronomy really started? There have been, I think that it's not really contested. I think it's pretty clear that Maxwell is one of the first that started looking at the possibility of radio signals coming from the sky. But it was only in 1933 when it was really considered the beginning and the start of radio astronomy. And this is when Carl Jansky discovered a radio signal coming from the Milky Way. Following that, fairly, not many years after, Greta Weber built the first radio telescope, which was the first actual, purposely designed radio antenna to study radiation from the sky that he built in his backyard. Many things happened in the years after that, obviously, but one of the most remarkable ones is that interferometry or radio interferometry began. And as I said before, the aperture synthesis technique is one of the most representative techniques for radio interferometry, developed by Martin Ryle, and which helped speed up tremendously observations of the radio sky. Eventually, we get to open our radio observatory here in Cambridge in 1957. Right, so the technology has changed quite a bit since the early days of radio astronomy. From left to right, we have an example of the first DIS radio antenna, the one that Greta Weber built in his backyard. In the middle, we have the IPS array, also known as the pulsar array, that is here in Cambridge, used to discover the first pulsar. So this is a collection of radio antennas that we can use to combine the signal detected by all of them, enhance our sensitivity and detect fainter objects. And then some of the first detectors and receivers at much higher frequencies, like the scuba detector on the very right. Things have evolved quite a bit. They are not substantially different in terms of what they are trying to do, but of course technology has evolved a lot, and that has translated into better technology also in radio astronomy. So we have gone through VLA, ALMA in terms of DISES, and the next big thing is the SKA MID telescope that will be in Southern Africa. In terms of arrays, at the moment, LOFAR, which has a station at Chepolton here in the UK, but most of the stations and arrays are in the Netherlands, is the current best example of arrays used for radio astronomy, and the SKA low instrument will be the next big thing, and this will be in Western Australia. And in terms of high frequency receivers, there are plenty of examples. So I won't spend much time today on them, but a lot of them installed in space-based telescopes, like, for example, JWST that was just launched a few months ago, etc. All right, so let me get back to the third point of the presentation, which is really the heart of it, and this is what is this scientific case that is pushing the construction of a lot of super radio telescopes like LOFAR at the moment, but also the SKA in a few years from now. One of the key scientific cases of the Square Kilometre Array telescope is the search for the light of the first stars, which is known as the cosmic dawn. Again, this is a cartoonish picture of the history of the universe, with the Big Bang on the left, present day on the right, and what we can see is how eventually the cosmic microwave background started traveling through the universe. But at the beginning, everything was very simple, everything was very empty. The universe was mostly filled with light elements, hydrogen, helium, etc. And this is what is known as the Dark Ages. Eventually, because of the effect of gravity, elements pulling together, the conditions were given for fusion process to occur, and the first more complex objects to form, like the first stars, which were born out of hydrogen itself, the most abundant element in the universe, right? And this is what is called the cosmic dawn, about 300 million years after the Big Bang. Right after the cosmic dawn came the epoch of reionization, and this is basically when the first stars and the energy emitted by these first stars shaped the universe completely, transformed the universe from the super simple volume, an empty volume during the Dark Ages, to the complex realm of celestial objects, star, galaxy, quasars, black holes, etc., that we know today and that we can observe today with optical telescopes. I will explain a bit later why we can actually observe all these objects with optical telescope, but we cannot really attempt to observe the light, the optical light from these very first stars. We can attempt, but it's why it is difficult and why radio telescope actually have a chance to do it. But basically, this cosmic dawn and this epoch of reionization is basically the epochs that are going to be studied by the Square Kilometre Array telescope, and they represent that. Okay,
I found this on the web.
Sorry, that's I think Siri. Sorry about that. They represent that missing piece in that history of the universe I was referring to. So what can we learn if we really try to study this? We manage to study these early epochs. We can learn about when and how these first celestial objects form. And as I was saying, how did they shape and transform the universe from very simple to very complex? Now, how do we do this? I will explain later why optical telescopes are probably not going to be able to do this easily. However, as I mentioned, hydrogen, the most abundant element in space, also emits a particular signal with a wavelength of 21 centimeter, 1.4 gigahertz. And due to the expansion of the universe, as probably most of us know in this audience as well, the frequency of this signal is redshifted, is moved to lower frequencies as it travels through the universe from the times of the cosmic dawn, from the times of the epoch of ionization until today. So a signal that was originated 400 million years after the Big Bang, right in the middle of the cosmic dawn, will be what we call a red shift of 13, and it will be observed today on Earth at about 100 megahertz, even though it originated at 1.4 gigahertz. Right, so what is this radiation that is emitted by hydrogen? I don't want to go into much detail here, but basically is a property of hydrogen itself. Hydrogen, the most simple and light element in the periodic table, a proton and an electron. If the electron and the proton spins are aligned, the energy of the electron respect to the proton is 1. When sporadically that electron changes a spin, and this happens for a given atom, once every a few 100 million years, but of course there are many atoms of hydrogen, so it's actually quite a process that happens a lot in the universe. But when the spin changes and it's anti-parallel with respect to the proton, actually this is a more stable configuration, which means that there is some excess energy that it's emitted at a frequency of 1.4 gigahertz, which corresponds to that excess energy that is not needed anymore to hold the electron coupled to the proton. Okay, so this is probably getting to the peak of the more sort of technical part of the talk, but I think it's important. So we have now learned why there is a radiation coming from hydrogen from the very early universe, how this radiation starts at 1.4 gigahertz and how it changes its frequency to lower frequencies because it travels for a long time in the universe. The universe is expanding, right? Now, how can we observe this anyway, right? So what we do actually is not observing this 21 centimeter signal, which is called 21 centimeter signal directly, but what we really observe is the imprint of this signal in another radiation that is traveling towards us and actually started traveling towards us earlier, which is the well-known cosmic microwave background. So we have the CMB traveling through the universe, eventually going through the hydrogen clouds, and then there are interactions between this spin temperature, the radiation of the 21 centimeter line, which has a characteristic spin temperature, and the cosmic microwave background, as well as the actual temperature of the hydrogen gas. So basically, if we summarize this a lot, there is the CMB temperature, let's say power of the CMB radiation, which is the blue line, and then we have the spin temperature, we have the gas temperature, this is the actual physical kinetic temperature of the gas, which can be colder or warmer than the CMB radiation temperature, and that 21 centimeter signal can either couple to one or to the other. So it can be trying to tend towards the gas temperature or towards the CMB temperature. And those variations, those differences with respect to the CMB temperature is what we can try to detect as a radio signal with telescopes today. Right, so just to summarize again, we have this 21 centimeter radiation that has a characteristic spin temperature, and that temperature can either couple to the gas kinetic temperature, to the actual physical temperature of the gas, or it can couple to the temperature of the background CMB radiation. And that the difference of the spin temperature with respect to the background CMB is what we can try to observe. And if we look at a plot of power or temperature with respect to frequency, it will look something like this, right? And these ups and downs of the signal is what we can interpret as we can try to understand whether the gas was colder than the CMB, or then it was hotter because there were more stars in the universe and they were heating up the gas, etc., etc. So let me tell you a bit about this, actually. Again, same plot. On the left, the Big Bang, on the right, present day, going through the cosmic dawn, going through the epoch of reionization, eventually getting to more recent times. And what you see here is that expected, but not detected yet, 21 centimeter line, which is this variation across frequency that can be used to interpret the physical processes that were happening during the early epochs of the universe, from about 10 million years to almost 1 billion years when the epoch of reionization ends. And we can see here a few ups and downs. So let me explain what they represent. At the very beginning, so just after the cosmic microwave background was emitted, we can see there is this sort of absorption, we call. So the spin temperature was lower the gas temperature, was lower than the CMB, which is always the zero line here. So you can imagine the CMB being this zero line, and the spin temperature was coupling to the gas because there were many collisions between particles. At that point in the universe was very dense, so particles were clashing with each other all the time, and that meant that the hydrogen 21 centimeter radiation was, the temperature was coupled to the gas temperature, and we can see this absorption. Eventually, the universe was less and less dense as it expanded. Therefore, those collisions of particles were less and less, happening less and less. And what we see is that 21 centimeter line should eventually disappear. However, with the formation of the first stars, that cosmic dawn, what we can see is that there are new mechanisms of radiation, and there is a specific one that I'm not going to be explaining here, but it's called Lyman alpha radiation. Maybe some of you know about it. And this Lyman alpha radiation from the first stars can actually help to couple again that spin temperature from the hydrogen emission to the gas temperature, which now it is even colder because the universe has expanded more, is less dense, and is colder. And then it's when we expect to see this, again, absorption trough here. But eventually, there are enough stars and enough galaxies in the universe that their energy is actually starting to heat up the gas. So what we see is that the process reverses, and that we expect that the lines start to go up as the gas gets heated. And eventually, that gas, that radiation from the new stars, the new galaxies, doesn't only heat up the gas, but it also ionizes the hydrogen. So it's basically helping to give energy to those electrons in the hydrogen in a way that eventually that those atoms of hydrogen cannot take any more, let's say, and they are ionized, and we cannot see this 21 centimeter line anymore, right? And this is when we consider reionization to end. Now, why is this not been done yet? Well, the reason is that it is super difficult because we are talking about signals. If you look at this vertical axis, we are talking about maybe 50 or 100 millikelvin, which is a measure for radiation temperature. This in contrast with the signals emitted by galaxies and stars that are nearby us in time is up to 100,000 weaker. So the so-called foregrounds, which are all the radiation happening, emanating from galaxies closer to us, are about 500,000 times brighter. Therefore, detecting that signal, that very faint signal from the early universe, is super difficult. Okay, so let me now tried to do something that I would have definitely appreciated someone would have done with me when I started in this field, which is try to explain and summarize what I just discussed from a more physical point of view with an analogy, right? And with a more sort of easier way to understand what's happening. So again, at the left, we have the Big Bang. Then at the right, we have the present day. So this is a timeline, right? At the left, we have clouds of neutral hydrogen. And we can see some stars forming here. So this basically is the cosmic dawn. On the right, we have ionized hydrogen. And then what we can see is all these stars, galaxies, and everything we can see with our optical telescopes from Earth today, right? These are closer to us in time, closer to us also physically in distance, and their light can be observed by optical telescopes. So these first stars, as I explained before, were actually born out of the neutral hydrogen, right? It was neutral hydrogen that was forming those first stars. Those first stars emitted light. However, neutral hydrogen is very good at absorbing short wavelength light, right? So that light from the first stars was absorbed immediately by the hydrogen clouds of the early universe, and therefore we cannot see it today from Earth with optical telescopes. So how can we see it? And again, this is coming back to what I was explaining before. At the Big Bang, we have the cosmic microwave background, eventually decoupling and started traveling through the universe. And the cosmic microwave background, as it traveled to the universe, you all have these radio signals that are also redshifting to lower frequencies. And then we have that 21 centimeter line, which is associated to the radiation from the hydrogen atoms in those clouds at the cosmic dawn. And we have the gas temperature and the spin temperature, and we could see that the spin temperature was either coupling to the gas or to the CMB. And this radio wave, actually, which is a sort of re-emission from this cloud, can be seen by radio telescopes because it was not absorbed by the neutral gas as the optical light, shortwave light was. So the analogy is that it is similar to what happens with a cloud when it's covering a landscape, right? It's the analogy of the fog, right? If we have a landscape, we have light from the sun hitting the landscape, reflecting to our eyes, we can see the landscape. If there is a cloud that is covering things, we cannot really see the landscape directly, but we can see the shadows that are casted in the cloud because of the backlight, and we can try to infer what the landscape looks like by looking at those shadows. And that's basically what we are trying to do with 21 centimeter cosmology using radio telescopes instead of our eyes. Now, let's make it even a bit more complicated because, of course, I did a trick here, which is that I removed all of these more recent galaxies and stars that we know of with optical telescopes to explain about this radio signal. But they are there. And this is what we call the foregrounds, right? They are also emitting radio signals that are added to the CMB, that are added to the 21 centimeter line. And then that makes it really hard to detect that radio signal from the infant universe because the foregrounds are so much brighter. So what the square kilometre array is going to do is to measure and remove the foregrounds. It's going to do very accurate maps, very precise maps of those foreground signals. It's going to remove them from the data so that it can measure that 21 centimeter signal, that radio signal from the infant universe. So eventually we should be able to get one day to something like this, which is, well, an artist impression of how, you know, the first stars may have looked like. But this is still a few years away from us. So let me start talking about the SKJ and about telescopes, because there are two ways to really do a measurement of the 21 centimeter line. The first one is with interferometers, collection of antennas that we use in conjunction, take the signal from every antenna, combine them in a certain way, and that they are able to measure, to almost create an image of the sky in some cases, because they have resolution on the sky. They can study the spatial fluctuations of that 21 centimeter line. And then we have what is called a global experiment, which is done with single antennas or single dishes, in which we try not to look at the spatial resolution, but to look at the spectral variation of the 21 centimeter line across frequency. Examples of interferometers are HERA, for example, Hydrogen Epoch Reionization Array, which is a telescope with 350 14-meter antennas. You can only see 19 here, but today we already have 350, and it's making observations from the Karoo Radio Reserve in South Africa. Or the future Square Kilometre Array. This is again an artist's impression of how the SKJ low instrument in Western Australia will look like, where there will be 512 of these arrays, right? So you can see the size of the telescope. And in terms of global experiments, we are actually looking at very simple antennas like this one, which is in Western Australia. And as I said, they don't have any resolution in the sky, but they are very good at measuring variations across frequency. All right, so let's continue a bit more about the principles of radio interferometry and the SKJ. We need large dishes because we need to detect very faint signals, and the larger the dish, also the more resolution, the smaller the pixel of the image that it can form, right? So there are examples, several examples of very large dishes, some of them here in the UK, like the Lovell telescope. On the left, there is the GBT telescope in the US. There are a few different examples, but, you know, it's not exempt of problems. And this is an actual case that happened with a telescope in Greenbank that collapsed because of its own weight. And I think the lesson to learn here is that while large dishes are maybe simple to understand, and they have done really amazing science in the past, they are actually a very expensive way to build collecting area, to build large radio telescopes. Instead, what we can do is build many small telescopes that will mimic that very large dish that we would like to build, right? So if we can position these small telescopes in the right position and they are far enough from each other, we can actually get an equivalent resolution to a very large dish. And the reason why we spread the antennas in an interferometer over very long distances is that it enhances our resolution. So it's the difference between a blurry image and a very sharp image of the sky. And why so many of them? Because the more small antennas, the more area collecting photons from the sky, therefore we can detect fainter signals. So it's like increasing the brightness of the picture. Right, let me just move on. So the final part of the presentation, which is about the world's largest radio telescope, the Square Kilometre Array. I hope I have given you a good idea of one of the key science projects of the SKJ, the detection and study of this the light of the very first stars. But what is the SKJ, right? SKJ is a international project, is the equivalent to the Large Hadron Collider in high energy physics, but in astronomy. Many countries, huge budget to build the largest radio telescope in existence. On the left, you see an artist's impression of the instrument that will be in South Africa. And this is made of 256 15-meter dishes. And on the right, you see an artist's impression of the instrument that will be in Western Australia, which is, as I said before, 512 of of these collections of antennas that has 256 of them. So in total, there will be 131,000 antennas. Many countries involved and 3 host countries. South Africa and Australia will host the instruments. Reason being, they have very isolated areas, far from cities, far from radio frequency interference, which is one of the bottlenecks of radio astronomy, because if we have radio towers and TV signals and mobile phones, we will be detecting those signals and not the sky signals, right? But the 3 host country is actually the UK, and it's actually also the biggest gas contributor to the telescope. So the headquarters are here in the UK at Jodrell in Cheshire. Many different institutions across the world have participated in the design, are currently participating in the construction, and are expected to do science with the SKJ. It's a global endeavor. In the UK, several institutions, although most of the design work has been led from Cambridge, Oxford, and Manchester. Okay, let me just skip over this. I said already, so it will be in South Africa and in Western Australia. What I would like to do now, if that's okay, is to show you a short video. It's a couple of minutes only, which is the trailer for what the SKJ is going to be, and then you can also see some of the people behind the project.
What did the universe look like when the first galaxy?
How many gravitational waves are passing through me right now?
And for me, the most important, is there life out there?
The building will be the largest science facility ever built by mankind.
What we're talking about is 2 telescopes.
These are going to spread out over literally hundreds of kilometers. It'll stretch out beyond the horizon. Our site's the middle of the West Australian desert, far away from towns, radio interference. We're building hundreds of dishes in a remote location in the middle of South Africa. It's a hot environment, it's a dry environment. It's really tough.
Een project als dit kan alleen tot stand komen als wetenschappers wereldwijd met elkaar samenwerken.
We need astronomers to define the scope of the instrument.
We've got to get 500 engineers to work together over 20 countries in all time zones in the world.
It's like building a jigsaw puzzle, but the pieces keep changing.
Part A being designed in one place fits to part B being designed literally on the other side of the world.
We've already started. We've got antennas at the site. There's equipment on the ground in South Africa and Australia.
Imagine the amount of data that's flowing through the internet at any one moment.
Huge amounts of data.
That kind of level coming out steadily with about a terabyte of data per second.
We'll have a total of 100,000 kilometers of dedicated fiber within the observatory.
But the greatest computing burden is to take those data streams and to make sense of them.
Every year we'll be distributing up to 700 petabytes of data. There's this huge range of science we'll be tackling. There's the technology that needs to be developed to do that science.
Practically every subject of astrophysics can advance thanks to SKJ.
It's from science to technology to societal benefits. This is what engages countries.
SKJ is a project that will be used for 20, 30, 50 years. We want to be part of this fantastic adventure of the human mind.
Credo che siamo davvero alle porte del futuro. La scienza parla tutte le lingue del pianeta. Il suo linguaggio connette il mondo intero.
This signature is the real beginning.
I think people will look back and think this is the moment the SKA Observatory was created.
Right. Good. Well, I wanted to give you an idea of the magnitude of the project, right? So let me just continue now. I'm minded of the time, so I'm gonna probably skip through some of the things here, but focusing on the low frequency instrument, which is the one that will attempt this study of the infant universe. As I said, it will be 131,000 antennas. Each of them, it looks a bit like this. It's like a metal Christmas tree about 2 meters tall. They were designed here in Cambridge, actually, and they will make a sea of antennas in Western Australia. But even more impressive is the amount of data, as it was said in the video, that this telescope will collect, which, as you can see here, is equivalent to 5 times the estimated global internet traffic only a few years back in 2015, which is obviously mind-blowing. But antennas are only the tip of the iceberg. The rest of the telescope is underwater, and it's all the electronics, optical fibers, amplifiers, digital processing, and the supercomputers that will have to handle that amount of data. And the study of the infant universe is not only the only science that it's going to be done by the SKJ. Is probably one of the key ones. How did the first stars and galaxies form? But there are many others. What generates the huge magnetic fields found in space? What are other worlds made of? And studies, detailed studies of gravitational waves and beyond, right? The capabilities of SKJ are so large that it should be able to pick up an airport radar in an exoplanet, in a planet outside of the solar system. So it could potentially be used to do studies of SETI as well. So where is SKJ at? SKJ started in 1991. That's where most people point the real start of the first ideas and proposals. And it went through many different phases of pre-designs and design and pre-construction. The latest and more significant events are the signature of the treaty that started the Intergovernmental Organization in March 2019, the inauguration of the headquarters at Jodrell Bank in Cheshire in July 2019, and the official commencement of construction in June last year. So here we are, it's being constructed. We expect to start doing science with it in 2028. And to finalize, as I said at the beginning, I was hoping to convince you that it's worthwhile doing, and in my view, this summarizes why it's worthwhile doing. It's groundbreaking science, something that has never done before, and it can really advance our understanding of the universe in a way that no other instrument can do. It's about science diplomacy. It's about how we need to collaborate to really achieve this super science. It's not anymore about one country or one institute doing it. And in the process, there is a lot of things to gain, also in terms of human capital development and the everything we learn in collaborating with people across the whole world. But also the technologies, right? I mean, we just heard about all the things we need to develop to make the SKJ possible. This is a state-of-the-art technology. When we've been doing the designs, we were working with assumptions of how technology was going to look in 10, 15 years from the moment we were doing the design. So we have been advancing and pushing technology that can also be used for many other applications. And with that, I end my presentation. Thank you very much.
Thank you very much for that. It's been a very concentrated tour of the technologies and the promise that there is in the Square Kilometre Array. I'm just going to check for questions in the chat channel. So I'll give everyone a chance to unmute and ask, put their question themselves. If that doesn't work, I'll ask the question. So we have Peter Scott, that's rather a deep question. What's the difference between dark energy and... Peter Scott, do you want to put that question?
Yes, I was looking on the SKA website, and we've all heard about dark matter and its presence in the universe and how much there is of it and how little we understand of it. But previously I hadn't heard about dark energy, and I was just curious as to what the difference was between those two elements.
It's indeed a very deep question. Let me give you a very summarized answer. Also to say I'm not expert on dark matter and dark energy, but in essence there are three fundamental components that make everything in the universe: dark matter, dark energy, and ordinary matter, what we call baryonic matter, which is basically everything that has mass. The other two need to be better understood, and there are many projects, including the SKA, that are trying to gain an understanding of how dark matter and dark energy play a role in making the universe that we can observe. To summarize things, what dark matter does is give birth to the ordinary matter, if you wish, and sort of hold the universe together, while dark energy is what is speculated is what is fueling energy to allow the universe to expand as it is expanding, right? What they are actually is something that is not yet known well enough. But those are the roles that we speculate they have in making the universe we know.
Right. I mean, at the moment we've had measures for the quantity of dark matter. Are they able to quantify dark energy?
Yes, I think we are. Everything that is not baryonic matter, that is not dark matter, then it's dark energy. So it's in the few percent, right? We can check it out, but it's in the few percent of everything that is in the universe. As I said, anyway, it's not my field of expertise, so but yeah, it's still one of those things that need a lot more study.
Right, Colin Downey.
Hello, thank you. Very interesting talk. I was just curious, because you're using such remote sites, whether you're planning to use any solar power from these sites, or would that interfere with your signal, or do you not actually need much power at the collection point?
It's a very good question. Yeah, no, it's been part of the development of SKA, understanding how to deal best with the power required, not only for the electronics and the antennas, but also for the supercomputers. At the end, the supercomputers happen to be in cities, so in Perth, in the case of Western Australia, in Cape Town, in the case of South Africa, and then distributed across the globe. So the power for the supercomputers is mostly coming from the network, right? For the electronics on site, at the end, the solution that was considered to be the most, efficient was to connect to the network. Solar power was considered, other types of geothermal energy generation as well. I wasn't involved on those developments, but my understanding is that what was at the end of the day most efficient was actually to make the network reach these places and plug into the network.
Do we have any questions in the room? Okay, Deepali, if you ask your question, I'll repeat it because...
Okay. My question really is about the nature of the observations. The optical telescopes would obviously be taking in photons, because visibility of stuff that the optical instruments would absorb are photons. But I just wanted to understand, what happens in transitional phase between the different, between the infinite universe and the different phases that talked about. What happens to the emanations from the hydrogen, from the atoms? Because they stop emanating photons. Is that why, it's not visible optically, but
okay, if I could sum that up a bit, then she's saying that optical radiation is generally considered as photons, but radio radiation is not so viewed as that, although essentially it's the same thing. It's all electromagnetic radiation. So it's asking sort of how the differences between how we view it in terms of photons or not. Does that make sense? I'm being the middleman here, so I hope that makes sense to both of you.
Well, can I repeat my question?
Yes, well, what's the essence of it then?
Question is, what happens to the emanations from the hydrogen atom as it goes through different phases in history, in universal history of the universe?
That I don't understand. I can't.
So, 100 million years ago, it was emanating photons. 500 million years ago, it was not. So what happens to the...
Well, nothing has changed. Nothing has changed in that respect. I mean, that would be a change in the laws of physics. Yes, I mean, we have redshift because the universe is expanding.
Why does that affect the photon? What happens to the photon? I want to understand. Where does the photon go?
I'm not sure if I got everything because it's difficult to hear, but it doesn't really affect the photon so much. What the expansion of the universe in this context is affecting is the wavelength of the electromagnetic wave. And this could be at optical frequencies or at radio frequencies. Everything is light anyway. It's an electromagnetic wave, right? So what makes it an optical signal that can be seen with our eyes, or it makes it a radio wave that can be detected with radio antennas, is the actual frequency of the wave. And what the expansion of the universe does is, because the universe is expanding, everything inside of it is expanding, including that wavelength of the wave. Therefore, something that started at a certain frequency, whatever it is, in this case 1.4 gigahertz for the hydrogen signal, it will go to lower frequencies as it travels through the universe.
Does that help? Okay.
Yes.
All right. If I could go back to Peter Scott, your second question.
Yes, I was really curious looking at the actual formations of SKAs and the implication that a solution which was more of rather like a galaxy, actually, in terms of spiral formation, was going to be the most effective way of actually capturing signal. Is that something that you could perhaps just explain to us why that would be the case?
Right. I guess you are talking about how the antennas or the stations are arranged, right? They are in sort of a spiral arms in the ground. So this is related to that aperture synthesis technique that I was referring to at the beginning of the talk. The way the telescopes work is because of their distribution in a radio interferometer, because of the distribution of the antennas on the ground, you are combining the signal from pairs of antennas, right? And what you do is, because of the distance between the two antennas and the orientation of that vector that links the two antennas on the ground, you can be more sensitive to certain directions in the sky. All right? Because basically what you are doing is, there is a signal coming from the sky. It is first received by one antenna. because it's coming from that direction, and then sometime later is received by the other antenna. Because we know the distance between those antennas and their orientation with respect to the sky, we can know what we expect that delay to be for a wave traveling at the speed of light, right? So now, by having many different pairs of antennas, we can sample different directions from the sky, right? So we try to design our instruments in a way that we have, we cover these different directions in the sky by selecting optimally the orientations of the antennas and the positions of the antennas on the ground. Why a spiral is good, I'm not saying it's the ultimate best, but it's a good one that was chosen for the SKA, is because on top of that, we use the fact that the Earth is rotating, and that every time that it rotates, we see a slightly different part of the sky, right? So what a pair of antennas were measuring a signal from this direction, as the Earth rotates, they are measuring a slightly different direction. And when you put all of that together,
I was going to say that the early sort of radio telescopes were bowls and had circular arrays, which were quite limited. But obviously, this is a way of maximizing the extent of the overall antenna and really doing it in the most efficient way, is what you're saying.
That's right, yes. We have a limited number of antennas, and we try to optimize how fast they can survey the sky.
That makes sense. Thank you.
By the way, I just found the exact numbers relating to your previous question. Dark energy, 68.3%. Dark matter, 26.8%. Ordinary matter, which is what we see and touch, is only 4.9%. So the dark energy, that is the one I think you were more inquiring about, makes most of the universe, and it is what is really fueling the universe for its expansion.
So it's still there and we're still growing.
We're still growing at the moment.
Thank you.
Okay. I'd like to ask you about the geographical distribution of the SKA. I mean, we've got Western Australia and we've got the Karoo Desert in South Africa. Are there other locations as well?
For the antennas, not. So this was decided back in 2012 that Western Australia and South Africa will be the locations of the antennas, and the headquarters will be in the UK. In the early days, well, not maybe early days, but during the 2000s, there were many different countries that were bidding to be the location. I think at the time there was China, there was, I think, Brazil and Argentina, even Chile at some point. There were a few countries, right? For different reasons, at the end, Western Australia and South Africa were selected.
All right. And do those two sites, can they work together as like a super interferometer?
They can, but they don't, because they have different technology. So the one in South Africa is looking at higher frequencies and different science cases. The one in Australia is operating at lower frequencies. And one of the main science cases is this study of the early universe. Potentially they could. I mean, we know how the picture of the first picture of a black hole, right, was made using antennas all over the planet. So potentially we could. But it's not how SKA is going to operate.
Right. Okay. I have another question here from Deepali.
My question refers to the location of these antennae. They both seem to be, both the locations are in the southern hemisphere. Does that affect, does that in any way affect the information that can be received? I mean, what about information that?
Okay, that sounds like a good question to me. So the question was, both the sites are in this. Your question was, correct me if I've got it wrong. Both the sites for the SK for the SCAR in the southern hemisphere. Does that limit the amount of the universe that it can observe?
It does. It will. The SKA will be observing the sky visible to the southern hemisphere of Earth. So it will not be able to observe certain parts of the sky that are only visible from the northern hemisphere. Yeah.
Because
Yes.
Related to that question is the fact that most of the constellations that we are aware of today, that we can see optically, happen to be visible from the northern hemisphere.
Well, I'm not sure about that. Yeah, I mean, you can't see the Southern Cross from the northern hemisphere.
So I'm talking about proportions.
Sorry?
Proportions.
Oh, right. I mean, you've got our two neighbouring dwarf galaxies. You can both see the Magellanic Clouds. You can see from the southern hemisphere. But I mean, you know, we're looking here at great distances anyway, far further afield than the stars that we can see in constellations. So
I think I got the question. I mean, I don't think we can say that there are less stars or galaxies visible from the southern hemisphere than there are from the northern hemisphere, right? Most of the sky is made by the Milky Way, the one we can see easily from Earth anyway, and then outside of it is probably more, it is quite homogeneous, right, in terms of distribution. What is true, though, is that the southern hemisphere sky has been a lot less studied at radio waves than the northern hemisphere sky, because in the early days, most of the radio telescopes were built in the northern hemisphere, right? Therefore, we know a lot more, especially about the radio sky, but also the optical sky that is visible from the northern hemisphere.
Oh, that's interesting, yes.
So my question, can I add to my question? The
Right.
optical universe is more prevalent in the northern hemisphere. Is there a reason for that?
Well, okay, well, I'll put that, but I doubt that myself. So the questioner thinks that there is
The
more.
optical universe is more prevalent in the northern hemisphere.
The optical,
Is there a reason for that?
the optical universe is more prevalent in the northern hemisphere.
Is there a reason?
Is that, first of all, is that true? And if it is true, is there a reason?
Yeah.
One thing I might have missed what the question is, but I don't think that's the case, really.
Yes, that's rather what I thought. Jonathan, can I go with you?
Yes, so the fascinating talk, but from a layman's point of view, and I guess this is true of other major projects, it fascinates me at the end of the process with these giant supercomputers, exactly how that information is going to be processed and who and how people will access it.
So he's asking, you're going to get a lot of data, big data you mentioned, from all this. How is it going to be processed and who will access it?
That is it's one of the challenges, right? With SKJ, we are talking about such an amount of data that the processing is super complicated. I mean, one of the main bottlenecks or challenges for SKJ is the storage of data as well as the transfer of that data. But transfer of data is more or less possible with the technology we expect to have. The storage of data is almost impossible. We won't be able to pay for it. There may not be enough storage to store all the data. So the way it's going to happen is that we are going to be reducing the data, basically combining the data and selecting the useful products that need to be taken forward to make the images, to make the science. And we're going to be throwing away most of the data, right? So we are only going to be keeping data for about 6 hours after it's taken. You know, I'm generalizing a bit here. It's not true for every science case, but mostly that's what we're going to be doing. And then just retaining some small amount of the data. Even so, that's a lot of data. So there is a whole effort in building what are known as regional centers. So in every region of the world, and the UK is one of them. Then there is one in Europe. There is one in like Asia, Australia, one in North America. You know, they are building their own infrastructure to handle the data that will come, right? And how do we store it? How do we distribute it? Mostly cloud computing, right? People will be able to log in from their computer into a supercomputer that might be somewhere in the UK, right? So that the actual work is done in the supercomputer from your terminal. But it is one of the big technological challenges, yes.
Yes.
One of the slides you showed was a nice impression of one of the first stars. If the SKA gets to that level of resolution, what sort of questions will that answer about the formation of the very first star?
I did cheat there. It won't have that resolution to make a picture of a star like that, right? It doesn't have the resolution. It won't have the resolution. It will be able to show us very zoom out images of regions where stars were being born, and then we can try to understand first of all how fast they were being born from the dark ages, and you know through these clumps of hydrogen, the stars forming, what sort of energy those stars were producing. Were those first stars different from the stars we have today? I mean, there were what is known as population 3 stars, which is supposed to be the earliest stars that were they had not metal in them, because at the beginning all the chemical elements in the universe were very light elements like hydrogen, like helium. So those first stars almost didn't have any metal in them. We expect that to be the case, right? While today's stars, they have plenty of metals in them, right? So we will learn about all of those things by understanding how they radiated, what sort of radiation they produce, and they were heating up the gas around them, etc., etc. But making a picture like that one I saw is not going to be possible with SKA now.
Right. I think we may have come to the end of questions now, and the last chance for anyone to put one in which case I'll say very big thanks to Eloy de Lera Acedo. This lecture is something to compare with one we had recently about the James Webb Space Telescope. I mean, this is another technology which is looking back even further to the beginning of the universe, and really it should be celebrated just as much, if not more, because it's going to do fantastic science. So if everyone could unmute and show their appreciation, that would be absolutely great. Thank you very much indeed.
A pleasure.
Right. Oh, thank you. I'm going to terminate the session now. So,
well, thank you very much for the opportunity. I've enjoyed it myself. So, thanks very much for that.
Thank you.